Okay, in this video we're going to finish off our solving trig equation skills, and we're going to look at our last two general types of trig equations that we'll encounter. So the one that we're going to start with today is at the bottom of your foldable, and it's when we have a quadratic function but the trig functions that are within it are different. What we saw last time is when we had the same trig function and we were able to factor those. So if you look into there, you can see how we factored those. What we're going to discover today is not all of our trig functions or trig equations are going to be written in that format, so we're going to jump into an example with that. So when I jump into this example, what immediately jumps out to me is that I have both a cosecant squared and I have a cotangent. Now that's problematic because I can't immediately factor this as I did in my previous example. So what I need to do is I need to rewrite this equation so that it has just a single trig function in it. It's okay that things are squared, but it either needs to all be in terms of cosecant or all be in terms of cotangent. Now, if they were both squared, it wouldn't matter which one we wrote it in terms of, but because my cosecant is squared, that's going to be the easiest one to do a substitution on using my Pythagorean identities. So I'm going to replace the cosecant squared, and I'm going to rewrite it so that cosecant squared is written in terms of its Pythagorean identity, and that would be shown as cotangent squared theta plus 1. So just thinking about our Pythagorean identities, that provides us a simple substitution. Then we can rewrite the rest of the equation, and we're now at least on to the idea that everything is now in terms of cotangent. Now, if you're comfortable solving with cotangent, you can move from here. If looking at that cotangent looks too complicated, we can do a simple substitution by defining a variable of y being cotangent. So we rewrite the equation as the square root of 3 times y squared plus 1 equals the square root of 3 plus y. Now we're just solving for y. It's just a simple quadratic here. I'm going to distribute my square root of 3. The right side isn't going to change. And now I can see that if I subtract square root of 3 from each side, my square root of 3's will cancel out. So now all of my c values have dropped out, so I'm going to move everything to the left-hand side. Square root of 3y squared minus y equals 0. I recognize this as a GCF problem, so I'm going to factor out my y, and I have square root of 3y minus 1 equals 0. So now, using my zero product property, I can come up here and I can say y equals 0 or y equals 1 over radical 3. Don't forget we need to back substitute, so we have cotangent theta equals 0 and we have cotangent theta equals 1 over radical 3. Of course, you could rationalize that if it is a little bit easier for you to picture that in your head. Either one is an acceptable way. So if I'm looking for where cotangent theta would ultimately equal 0, I'm trying to think where in my unit circle would cotangent evaluate to 0, and that's going to be at the top and the bottom of my y-axis. So my theta value for this part of my equation is going to be pi over 2 and 3 pi over 2. When I'm looking at my second part of my equation, I want to know where does cotangent evaluate to 1 over radical 3 or radical 3 over 3. And first of all, I'm going to think all students take calculus. I need it to be positive, so I'm looking for what reference angle in this quadrant and what reference angle in that quadrant. This is going to evaluate at a 60-degree reference angle. So my theta value is going to be pi over 3 and 4 pi over 3. So again, the key on this problem is always look at your quadratics and make sure that they are written in the first or in the same type of trig function before you try to jump into any solving. Now, if we turn this foldable over, we're going to look at a very special case, and the special case is going to be how are we going to handle when we have multiple or partial angle rotations. What we could have in here could be something much more complicated than a 3 theta. Later we'll learn some double angle identities and some half angle identities that might make some of these a little bit easier, but we're going to go ahead and look at a longer process for this. So the first thing that we want to understand is graphically what kind of an answer are we looking for here. So what you can see here on my graphing calculator is I have graphed a single period of sine from 0 to 2 pi, and what if this were sine of theta and I was looking for where it equaled 1/2, I would simply be looking for where does my graph reach a y value of 1/2, and I could see that it would cross this wiki stick in 2 places. Now, if I go back and then I graph sine 3x and I graph this one on the same grid, what we're going to see is since it's moving 3 times as fast through the period of 2 pi, I now am going to have more answers for my y value of 1/2. So now when I put my wiki stick down here, what I can see is it's going to reach this value of 1/2 1, 2, 3, 4, 5, 6 times. So I need to find all 6 of those angles. So that's ultimately what we're looking for here. So when I jump into this problem, the first thing that I'm going to do is I'm going to simplify it. I'm going to do a little bit of a substitution. I'm going to define my variable of y as 3 theta. So I can rewrite this problem in its simple form. So I want to know where is sine of y equal to 1/2. Again, I'm just thinking on my unit circle, I'm looking for positive values for sine. That's going to be in my first and my second quadrant. The reference angle that would give me a value of 1/2 is going to be 30 degrees. So my y values are going to be, let's write a y there, sorry about that. My y values are going to be pi over 6 and 5 pi over 6. And those, of course, make sense with the graph that we just saw, the original 2 values. Now, we weren't, of course, asked to solve for y, and we weren't asked to solve sine of y equals 1/2. We needed sine of 3 theta. So now what we can do is we can go back and we can say, okay, separate these into 2 problems. I'm going to say 3 theta could equal pi over 6. And then what I want to do is I want to write this in a general form. So I want to include the full rotation of 2 pi times k, where k could be any integer. That's going to allow me to find these multiple repetitions. I'm going to solve this for theta. So I'm going to multiply through or divide through by a third, whichever way you can divide by 3 or multiply by a third. So my theta value equals pi over 18 plus 2 pi over 3 times k. Now what we're going to do is we're going to go through what are called iterations of k, and we're going to find what are our final answers for theta. So I'm going to first assume that what if k just equaled 0? What if k was just a simple 0? Sorry about the lighting on this video. See if I can get that fixed for you. So if my k value equaled 0, then I would have theta equals pi over 18. 0 times 2 pi over 3 is 0, and I would get pi over 18. So that's going to be my first of my 6 answers that I'm looking for. I'm going to continue this process until I get a value for theta that's more than a full rotation or more than 2 pi. So if k equals 1, I'm going to have pi over 18 plus my 1 times my 2 pi over 3, or just 2 pi over 3. Of course, I need those common denominators, so I can even jot it down, multiplying top and bottom by 6. So I now have 12 plus 1, or 13 pi over 18. That's my second value. Continuing on, I'm going to say k equals 2. This is a very repetitive process, and I'm going to let you finish the end by yourself. I'll let you practice those. So I have pi over 18 plus, now I'm going to do 2 times 2 pi over 3, or in other words, 4 pi over 3. Again, I'm going to need common denominators. Of course, you don't have to write that part down. So I have 24 plus 1, or 25 pi over 18. And when I get to k equals 3, you might already know where this is going, but when I get to k equals 3, I'm going to have pi over 18 plus, and when I do 3 times my 2 pi over 3, the 3's are going to cancel, so I'll get 2 pi, or I can even write it as 6 pi over 3 if you don't see that canceling. But what I can immediately see here is that 6 pi over 3 is a full rotation. So a full rotation, or 2 pi plus pi over 18, that's going to be outside the interval of the angles that I want. I want all my theta values to be between 0 and 2 pi. So since that's more than a full rotation, or more than 2 pi, I'm done with that angle. So I found 3 of my angles. I can finish off this problem by remembering that I have a second angle that I solved for up here that was a potential value for y. So now I can set 3 theta equal to that second value. You have to do these two processes separately. Of course, I'm going to add to that 2 pi k. I can divide by 3, or think multiply by a third, whichever one you prefer. And when I do that, I will get theta equals 5 pi over 18 plus 2 pi over 3 times k. And after that, you're just going to continue doing the same iterative process that you did on the previous example. So if you follow that process, solving for your k equals 0, 1, 2, you will find that at k equals 3, once again, you'll exceed. And sure enough, we found all 6 angles that we needed.